Assalamualaikum and good morning. Okay, we proceed with the properties and the morphology of the crystalline polymer. Okay, crystalline polymer are formed in the melt by diffusion of molecule or section of molecule into closed pack or the arrays, and this then crystallize. Okay, as I mentioned earlier, the crystalline is actually high density polyethylene, for example. It prepared from a dilute solution, and we can observe the crystal formation in the solution when it become a crystal by using a microscope. So the crystal have a hollow pyramid shape, and the size is exceed 1 to 100 nanometer size. Okay, so the crystalline structure, it can produce a model called the fringe micelle structure. So it also has a chain folded model. We call it as a chain folded model because the chain can be folded. Okay, chain tu dia boleh lipat. Okay, so the crystalline structure, we call it as the fringe micelle structure. It has the regular with adjacent re-entry fold, irregular with adjacent re-entry fold of varying length, and the switchboard with non-adjacent fold entry. So, okay, we look at the structure, the shape. Okay, the most polymer don't stretch out fully like this. Okay, polymer dia takkan stretch out fully like this because the properties is it can fold it. Okay, dia boleh lipat macam ni. Instead they stretch out, they can fold back on themselves after going straight for a shortened distance like this. Okay, this is the folded shape. So we call it as the folded model or fringe micelle. Okay. Alright, they can fold and they can stack. A stack of polymer chain folded back on themselves, like this is called a lamella. Okay, so lamella consists of polymer crystallized, and it has a very thin platelet. Okay, so the chain fold back and forth within an individual plate. We call it as the chain folded model. So sometimes a polymer chain is indecisive and part of it is in the crystalline lamella, but part of it stay outside the lamella in the amorphous region. Okay, this one is the amorphous region, and this one inside is a crystalline region. So this lamella have a chain that go out for a while, then come back in, right? So on the left, the chain re-enters the lamella, right, next to where it left. On the right, our outgoing chain come back in some distance away from where it left, but both are possible. And these two pictures both show what is called the switchboard model of a polymer crystalline lamella. So the folded chain might be these two shape, right? It has the amorphous, and this one is the crystalline. This one also amorphous, and this one is the crystalline. Okay, we look at the semicrystalline polymer. Okay, semicrystalline polymer is a polymer who's having lacking positional order section, which has amorphous behavior and packed adjacent chain entry ordered structure, which called as a crystalline behavior. So semicrystalline polymer exhibit amorphous and crystalline region. Okay, for crystalline polymer, it has 100%, but we cannot have the 100% crystalline unless we produce it in the lab, right? So most of the polymer has a semicrystalline structure. Alright, look at the factors influence the morphology. We have the intermolecular bonding, the symmetry, the tacticity, and also the branching. Okay, we look at the details of it. First, we look at the symmetry. Okay, what is the symmetry? The symmetry of the chain shape influence the ability to form crystalline. So the symmetry is like we noticed in our previous slide, which is the linear, right? Apa nama? Isotactic, syntactic, okay, linear ataupun linear or branching polymer. Okay, so the linear symmetrical molecule are the best. Okay, if the linear means the isomer. Okay, isotactic, bukan isomer, isotactic. Okay, iso the configuration is on the same side. Okay, for polyethylene, polytetrafluoroethylene and other chain with more complex backbone containing O, COO and CONH group all possess a suitable symmetry for crystalline formation and usually assume a standard zigzag conformation when aligned in the lattice. The chain containing irregular units, okay, which detract from the linear geometry reduce the ability of polymer to crystalline. Okay, so kenapa maksud dia kat sini macam ni? Okay, because the polymer which is has the easily to crystallize it has a regular structure. So for the chain containing irregular, uh, it is difficult for them to crystallize. Okay, for example, cis double bond O and M phenylene group and cis oriented Park ring. So all encourage bending and twisting in the chain and make regular close packing very difficult. So, for example, as we mentioned in our previous week, we have trans natural rubber, right? Trans polyisoprene. So, trans polyisoprene has the ability to crystal to be highly crystalline. Okay, compared to cis 1,4 polyisoprene. So, same goes to the regular. Okay, if the polymer have regular structure, so the ability to crystalline or crystallize is high. Okay, compared to irregular. Okay, hope you don't confuse. Okay, in terms of the intermolecular bonding, the close packing, which is the crystallinity achieved by the chain, allows the van der Waals forces to act cooperatively and provide additional stability to the crystallite. So, any interaction between the chain in the crystal lattice will help to hold the structure together more firmly. The polymer containing polar group can be held rigid and aligned in a polymer metric by the strong dipole-dipole interaction or the hydrogen bonding between the substituent. So the crystallinity also affected by the intermolecular bonding. So as we all know, intermolecular and we also have intramolecular forces. Okay, for intramolecular forces we have primary forces, and for intermolecular forces we have secondary forces. Okay, so the intramolecular forces, which is the primary forces, we have the covalent bond, ionic bond. So for secondary forces, which is intermolecular forces, okay, we have a van der Waals, hydrogen bond, and also dipole forces. Okay, the secondary forces, it have a effect on many of the physical properties of polymer. Okay, like crystallinity, thermal transition, and also melt viscosity. So, van der Waals, dipole, and also hydrogen bond, very important. Okay, because it will affect the physical properties, thermal transition, crystallinity, and viscosity. Okay, so let's look at the other slide. Right, intermolecular bonding in polymer. Okay, the bonding give rise to the molecular cohesion and resultant in crystallinity. Okay, so we call it as a intermolecular bonding. Just I mentioned earlier, we have dipole, van der Waals, and hydrogen bonding. So for polymer, we have a non-polar polymer, for example, polyethylene, polypropylene, and for polar polymer, which contain OH substituent group, we have nylon. Okay, so for non-polar polymer, the forces or the intermolecular bonding exists is a London forces, and for polar polymer, we have dipole-dipole interaction, hydrogen bonding and also the ionic bonding. So dipole hydrogen and dipole interaction and hydrogen bonding is secondary forces, and the ionic bonding is the primary forces. Okay, so we focus on the dipole and hydrogen lah, because the dipole and hydrogen and also the van der Waals is very important, because it affect the thermal crystallinity and melt viscosity. Okay, this is the intermolecular forces in polar polymer. Mana A? Tak ada pun A. So this is the B. B is the hydrogen bonding in polyamide. Okay, this is the hydrogen bonding, and C in a carboxyl containing polymer. Okay, we can. I don't know where is this the other structure, but it's okay. Okay, in terms of the tacticity, the chain symmetry and flexibility both affect the crystalline of a polymer. Okay, the large pendant group increase the difficulty of close packing to form a crystalline array, and the problem with large pendant group can be overcome with the arrangement the group in a regular fashion along the chain, which is the isotactic, syntactic, and atactic. So means that the tacticity, which is the isotactic, it has high properties of crystalline polymer. So the isotactic arrangement tends to produce highly crystalline polymer. The compared to syntactic, okay, syntactic also can produce highly crystalline polymer, but it's less than isotactic. And atactic, it produce amorphous polymer. Okay. So the for isotactic polymer, just I mentioned earlier. Okay, for the isotactic, which has high crystalline, it has high rigidity because it is less flexibility. Okay, and the tacticity means the high rules, high influence, okay, on the flexibility. For atactic, it has a amorphous region mostly and highly flexible compared to isotactic and syntactic. So iso is the most rigid, and the melting temperature is high compared to syntactic and atactic. Okay, so isotactic also less affected by solvent penetration. Alright, compared to atactic and syntactic. Okay, so look at the branching. The effect of the branching on the crystalline polymer. Okay, the packing efficiency deteriorates and the crystalline content is lowered if the chain is substantially branched. So what does it mean? Means that if the simple polymer with little or no branching crystallize more easily. Okay, so whereas the crystallization is inhibited in heavily cross-linked polymer and in polymer containing bulky side group. Faham tak maksud saya? So maksud dia macam ni, kalau polymer tu dia ada sedikit, little, or tak ada langsung branching, dia akan lebih senang untuk crystallize. Okay, so simple polymer with little or no side branching, it will crystallize more easily compared to polymer with highly bulky side group. Okay, kenapa? Sebab kalau polymer yang branching, dia susah untuk bergerak. Kalau yang tak ada branching, less branching, dia senang untuk dia punya backbone untuk rotate, untuk bergerak. Okay, look at the other slide. The chain, bukan yang ni. Okay, the morphology of polymer are the most significant factor affect the thermal transition. Okay, so in terms of the thermal transition, completely amorphous polymer, we only show the reading for glass transition temperature only. For completely crystalline polymer, it will